so more or less works.
Okay, so let's start. I'm very glad to see everybody here. Every time a new location, I'm surprised myself. And we are going back in time. Now we're using Blackboard instead of fancy devices. I wonder what it will be next time. Yeah, this is a very cozy room. You can feel yourself at home. You can have some coffee over there. Hopefully, I don't know if there is any supply. Okay, so last time we attempted to derive a nonlinear sigma model, and we came to this expression, an action of a matrix Q, which is matrix Q, I just remind you, was a matrix, a rotated matrix lambda, and the rotation U, oh, sorry, this is not how it was written last time. It's the matrix T, not U. It's funny. It's T inverse lambda T, and T is a unitary matrix. It's an element. It's a unitary matrix of size 2n. N is the number of replicas. This board is actually very nice. Yeah, and in terms of this Q matrix, we derived the action. This happened. This matrix Q appeared when we did a Hubbard-Stratonovich transformation. Then we integrated out fermions, and we're left with a determinant that corresponds to a logarithm of this operator. And the last step, which was a bit messed up, was the gradient expansion of this logarithm. So expansion, assuming that omega is small and Q slowly changes in space. And the result of this gradient expansion is actually the nonlinear sigma model. This result looks like this. Pi nu over 4 integral over the whole space, trace d nabla q squared plus 2I omega lambda q. This, let me remind you, we had two small contributions, one with linear in omega. This omega is small. We expanded in omega, and it produces this term here after we take the trace, or after we integrate momenta in psi. We have omega times lambda times q, and the other term contained two gradients, so we expanded this in gradients of q up to the second order. We did again the integration over psi, and we had a term that combines into the trace of gradient q squared and has a diffusion constant in front.
Sorry, we probably meet the term with the q squared.
We did the calculation, and we had a term which contained gradient t inverse squared.
And this is the expansion of logarithm, but the full action has a q squared term in addition to logarithm.
Yeah, but that one was thrown away as long as we said that q has this form, so it becomes a constant. Q squared is 1. Q squared is just a unit matrix. Yeah, sorry. So this is. Okay, so this is the main object that we will study for all the next lectures almost. This is called the action. This is the action of the nonlinear sigma model, and it has a very nice form because it looks almost like the diffusion equation. We have d gradient square, and and time derivative, as it usually happens in the diffusion equation. Here, it's a similar object, but with a matrix Q. And this matrix Q is a very special matrix. It's not just anything. It's a matrix lambda rotated with a unitary rotation. So, for example, as I just mentioned, the square of this matrix is always a unit matrix. Lambda squared is 1, lambda is plus minus 1, so Q squared is also 1. Yeah, now a few important points. This action has certain symmetries. First, there is a global symmetry. You can take this matrix Q and rotate it by any unitary matrix. And since we have trace here, these rotations will just disappear. At least, sorry. No, probably it works only at zero frequency, of course. So for this term with a gradient, we have such a global symmetry, meaning that if U is constant in space, has zero gradient, and omega is 0, we can indeed do such a global global means that U is constant. So it's the same rotation in all points in space. And this is the same U that we call T here. So this group, U of 2n, unitary group of the size 2n, is the global symmetry. It's related to the symmetry of the original fermionic action when we can do this change of variables. Remember when we rotated the phi fields by arbitrary metrics, it's the same symmetry. We still have it here in such a form. And then there is also a local or gauge symmetry, which is not visible in this action. That's why I will not mention it right now. Well, actually, I will, sorry. Question. When we say that the Q matrix is like the matrix lambda rotated, how many of these Q matrices exist, actually? How big is the space in which this thing operates? Why do we need Q if we can instead work directly in terms of T? We can take this T inverse lambda T and insert it here everywhere, right? And matrix T is just a unitary matrix of a size 2n. It's a very nice object. We all understand how it works. It's 2n by 2n matrix. Has 4n squared elements. But it turns out that Q is a smaller space. So you can have different matrices T that produce the same matrix Q. And it's important that the action is written in terms of Q, so the action is invariant. If you take two different matrices T that correspond to the same matrix Q, you get the same action. This is the gauge symmetry that I'm talking about. And usually it's written in the following way. Just imagine that we have some matrix T which produces Q like this, and we change this matrix T, we multiply it with a matrix K. Just do this change. Then matrix Q also changes. It becomes T inverse, K inverse, lambda, K, T, right? And now I assume additionally that matrix K commutes with lambda. I take not any matrix K, but such that it commutes with lambda. Then this part in the middle is just lambda. They commute and cancel each other. So what I have is the original matrix Q. It didn't change. This means that if you have some matrix T and the corresponding matrix Q, you can always multiply T with any such matrix K, and Q will not change. So this is our gauge freedom. We can choose this K any way we like without changing the matrix Q. And what does it mean that K commutes with lambda? Lambda is a very simple matrix. It's 1 minus 1 in retarded and advanced sector, which means that K can be represented as K retarded, K advanced. Any diagonal matrix like this will commute with lambda. And these two matrices, K retarded and K advanced, they're also unitary, but of a smaller size. They are not 2n, they're just n. This one is un, and this one is also a unitary matrix of the size n. So this whole thing combined in mathematical terms is written like this. Matrix T belongs to the unitary group U of 2n, and the matrix K, the matrix Q, the Q matrix, belongs to the unitary group 2n divided by twice the unitary group of size n. This is called a coset space. So you have a set, many matrices, and then you say any two matrices in this set U, any two matrices T, that are related by this relation, I will call them equivalent. So this whole set breaks into equivalence classes. Inside each class, I have matrices T related by this multiplication with K. So each equivalence class is isomorphic to the product of two UN groups. And then I say that different Q matrices correspond to different classes. Within each class, the Q matrix is constant. It does not change if I change T matrix inside the same class. So that's called the space of right cosets of U of 2n. This is just it's like the factor group, but the only distinction is that this is not a normal subgroup. That's why this factorization does not provide a group. It provides some other mathematical construct which is called the coset space. It's called a coset space. So matrix Q belongs to a coset space, in this case to this one, and we should study how this action works on the space like that. Now, since we do have this diffusion equation almost built inside the action, we probably can derive from here the diffusion equation itself, and actually we can also derive all the quantum corrections that we studied before. Quantum corrections that do, for example, corrections to the diffusion constant. And this will be the next thing we will consider, the quantum corrections coming from this sigma model. I will show you how it works. Just another comment about this coset space. This is a very important part, very important to understand how this space looks like. What is this? It's a multi-dimensional space. Of course, it's hard to imagine literally, but still, just as an analogy, imagine we know that Q squared equals 1. So it's quite easy to imagine a unit vector, right? A vector whose square equals 1. It's a vector that lives on a sphere of the unit radius. So actually this coset space is some generalization in a multidimensional space of a sphere, of a usual sphere. And there are many spaces like this. This is just one of them. There is a whole mathematical term. It's called symmetric space. It's a coset space as a factor of one group by the other, but it's also a symmetric space because it looks like a sphere. Symmetric space. Symmetric space, yeah, I'm not an expert in mathematics. There are several equivalent definitions of what symmetric space is. And one definition, which is most intuitive, is a space of constant curvature. If you have a sphere, you look near any point and it is curved in the same way as near any other point. So a space of constant curvature is automatically a symmetric space. There are other definitions which are maybe not so intuitive but easier to check. Anyway, symmetric space is a space of constant curvature, and each point in this space, each value of Q, all of them are absolutely equivalent. You can rotate this whole symmetric space such that any point becomes any other point, and nothing will change. I mean, you can rotate a sphere such that any point becomes the north pole and nothing changes. So this is also true for all other symmetric spaces. So you can always think of it as a sphere, but in some multidimensional space, in some generalized form. And then this action tells us that Q matrix, it's a point on this generalized sphere, and it can somehow move around it with the gradients that cost some energy. And lambda, actually, lambda which stays here, is also a special point on this sphere. See? If the matrix T is a unit matrix, Q equals lambda. So lambda is just one of the points on this coset space. Usually I prefer to think of it exactly as a north pole of the sphere. So lambda is the north pole. It's a unit. Q is like a unit vector, and Q equals lambda is like a unit vector pointing up. And then when you apply these T matrices, you rotate it and you can bring it to any other point on the sphere, or you can rotate the sphere and make any other point equal to lambda. Lambda is just one particular point on this space. So this term here, it's like a potential energy. It tries to bring matrix Q to the north pole. It's like attraction to the north pole, but it's an attraction with an I here, so it's an imaginary energy. Sorry, that's how it does. And this is like a kinetic energy. It tells us how much does it cost for Q to change at all. I mean, this is like a kinetic energy, this is like a potential energy. Okay, so since we have a very limited board, and it's not easy to erase anything, I will try to squeeze all the information. So what we will do with this sigma model, we will see how the usual diffusion equation comes out of this action, and how can we compute quantum corrections. And this whole topic is called perturbation theory. So it's a complicated nonlinear action. It cannot be solved analytically in its full form. We should do some approximation to solve it. And one possible approximation is the perturbation theory. Perturbation theory. Yeah, and actually the parameter for this perturbation theory, we will see it later what the actual expansion parameter is. I can tell you that, sorry, any question? For now, I can tell you the actual parameter will be the conductivity. Conductivity, you remember, according to the Einstein relation, is product of nu and d. This is nu, this is d. So the prefactor of this gradient term should be a large number. This will be the parameter of our perturbation theory. We will see it in the end how it appears. Yeah.
So far, we actually used only two approximations, right? First, when we decided that we can actually use a saddle point approximation.
Yeah.
And second, when we decided that there is a small gradient.
Gradient expansion.
Yes. So can you, for the sake of clarity, consistency, just write down formally the small parameters that we actually need?
Okay, let me put it this way. Imagine an axis which has a name. I will call it length scale. This is a scale for length. And on this axis we have different scales. The shortest possible length in a metal is what? Who can?
1 over Q.
What is the shortest possible length?
Interatomic distance.
0 is the shortest possible length. Yeah, actually 0 is the shortest, but after 0, the next meaningful length is the Fermi wavelength, lambda Fermi, which is, in most metals, the same as interatomic distance. And then, if we have a disordered metal, there is another length scale, which is the mean free path, the scale up to which the electron can propagate freely before it gets scattered. And usually this mean free path is much longer than the Fermi wavelength, otherwise it would not be a metal. And this distinction between Fermi wavelength and L, this huge, the large window here, is the parameter that we usually call semi-classical parameter, or we do semi-classical approximation. This is when we fixed q squared equals 1, when we did saddle point, we used this inequality.
So physically, we assume that there are like quasi-particles, well-defined quasi-particles.
Not just well-defined, they can propagate almost classically to a long distance before they start being scattered. And then if we go to a longer distances, what happens at a distance larger than L? Actually, diffusion sets in. So everywhere here, what happens is diffusion. And what happens on this scale is called ballistic. It's where electrons propagate as just free particles along straight lines. This is a window for ballistic transport or ballistic physics, and this is the window for diffusion. It extends up to infinity. So first we used this distinction between these two scales, that lambda Fermi is much shorter than L, to fix q squared equals 1. And then when we say, let's assume omega is small and gradients are small and do the gradient expansion, it means we assume that the length scale at which we work is much longer than mean free path, that we are well inside the diffusion limit.
So you mean like
I mean that the size of the sample is much larger than the mean free path, or the frequencies at which we work correspond to the length scale that is, so square root of d over omega is much larger than the mean free path. This is the same thing. Yeah, so if we are well inside the diffusion regime, we can say that gradients are really small compared to the mean free path. Frequencies are small compared to that, and then we can do this expansion here. So sigma model is an effective model that works in the diffusion set of scales.
So in the same manner, we can just put like L big and
yeah, we can say that there is some scale L at which we do our measurements. It's like the infrared scale, and it should be again much longer than the mean free path.
And this is for the gradient expansion.
Yeah, so this is for the gradient expansion. This is for q squared equals 1 for the saddle point.
And what will be the parameter of quantum corrections?
As I just said, the parameter will be the large parameter. So the corrections will be inverse to it. Nu times d is the conductivity. This is not yet visible, and it has nothing to do with this scale here. It will be seen later today, hopefully. Okay, so perturbation theory. Perturbation theory means we should select something which is our zero order approximation and then expand near the zero order approximation. And perturbation theory is actually an expansion for the matrix Q which almost equals lambda. Just imagine for some reason this is the minimum of the action, right? Q is constant, this gradient is zero. And which constant, actually Q equals lambda, will minimize also this term. So Q equals lambda is some boring minimum of this action, boring because Q is constant. And then we can expand near this minimum and have some Gaussian theory or some non-Gaussian corrections. And this will be exactly the perturbation theory that it's the easiest thing you can do here. So you can think of it again. Q lives on the sphere. We have a sphere. Lambda is the north pole on this sphere. And when Q is almost equal to lambda, it lives somewhere near the north pole, not going very far from it. So it means that the matrix T in this definition should be almost a unity matrix. Unity matrix is also unitary, and unity matrix corresponds to Q equals lambda. So we will say that T is almost a unity matrix, and then there is some small correction to unity, which we call W over 2. W is also a matrix. And then there is a next correction, plus W squared over 8. So there is some series. We have, this is our zero order approximation, linear, quadratic, cubic, and so on. And actually, this is a definition of the matrix W. So T is just a unitary matrix. And I would like to say that it's close to unity. And I expand it in some small matrix. So W is small, much smaller than 1. And the way I do this, I can select any coefficients here, actually. The way I do this, just to trick you, it was a trick. It's an expansion of an exponential function. It's exponent of W over 2. So this is how you can do the same thing reverse. You know that T is a unitary matrix. Any unitary matrix can be represented as an exponent of anti-Hermitian matrix. W is anti-Hermitian. It changes sign under Hermitian conjugation. If W is anti-Hermitian, its exponent is unitary, and I will represent T as such an exponent. And then to have T almost equal to 1, I will say that W is small. It's almost equal to 0. Then this exponential can be expanded in a power series, and these are just the first 3 terms of such an expansion. Now, what does it mean for the Q matrix? Q matrix is T inverse lambda T, so it's exponent of minus W over 2 lambda exponent of W over 2, just this product. And I can also expand this product in power series in W. And you will see in the lowest order, when W is 0, it's just lambda. And the next term, I can pick up W from here or W from here. It's 1/2 a commutator of lambda with W. And then plus, there are other terms. Probably you even know how they look like. It's a commutator of commutator of commutator. It's just a series in commutators. So what's important here is that if W contains some part that commutes with lambda, this part will just drop, at least in this linear order. It will not contribute to the Q matrix. So I can add another requirement. I will say that W should anti-commute with lambda, just such that I do not include any variables inside W that are non-physical, that are non-observable. You see, if W contains some part that commutes with lambda, this part will drop from here. It will not change the Q matrix. So I can assume from the very beginning this part was 0, and the only thing remaining in W anti-commutes with lambda. Just a reminder, any matrix can be split into part which commutes with lambda and which anti-commutes with lambda. This is just a linear, these are two linear spaces that are orthogonal. So, for my perturbation theory, I will say that Q matrix, that T is like this, Q is like this, and actually if W anti-commutes with lambda, it means that I can take this exponential and put it on the right with change in sign of W. So what's written here is just lambda exponent of W. I have used here the fact that they anti-commute. And that's why I had W over 2 here, because I wanted to have no coefficient in this expression.
Anti-commutation requirements only needed when we use the first order.
Yeah, let me give you an example. Imagine a sphere at the North Pole. You live near the North Pole, lambda is what points out. And then you apply some rotation. There are 3 types of rotations. One towards east, one towards whatever, 90 degrees from east, and the third one is around z-axis, which does not change lambda. So I say in my linear expansion, I have to keep only those 2 directions that do not commute with, which do not conserve this pole. Now, when I selected these 2 directions from the North Pole, I can exponentiate them, and actually I recover the whole sphere.
So formally speaking, if we just take the next order in W, we will still have some commutators.
Yeah. Well, it's a bit trickier than this, but the overall result stays. So if you select W such that you do not overcount the number of directions near the North Pole, it's enough to reproduce the whole space. Yeah. You can count how many variables you have inside W, and you can count how many variables you have inside such a matrix, and you will see that they are equal. You have a 2-dimensional sphere, and you have 2 directions from the North Pole to recover it, to construct all possible points starting from the North Pole. Okay, so perturbation theory means doing this expansion in powers of W, and let's do the expansion. Yeah, and actually let me write the third equation. I have these constraints. W must be anti-Hermitian and anti-commute with lambda. So I can write this matrix W explicitly, and I will write it like this. B minus B dagger 0. This matrix is anti-Hermitian, yeah, because when you conjugate it, B becomes B dagger, and I have minus here. And this matrix anti-commutes with lambda because it's off-diagonal. Lambda is 1 minus 1, the diagonal matrix. This one anti-commutes with lambda. So as long as I selected W of this form, I automatically satisfy both conditions. And this B can be any matrix. There are no restrictions left. So B is an n times n complex valued matrix, and this one is the conjugate of the same B. So this B dagger, they are related by Hermitian conjugation. So a little exercise, which I will not do on this board because I hate it, the board I mean. But it's easy, so you can do it yourself sometime, maybe even now. If you take this W, insert it in this expression, let me write it explicitly. For the Q matrix, it's lambda 1 plus W squared over 2. Expansion up to the 2nd order. It's just this exponent expanded once again. So you take this W, insert it here, get the matrix Q, and then insert it in the action. and you keep only terms linear and quadratic in B, because we expand up to some low power of B or of W, what you will find is that there is no linear term. This action starts from the quadratic term of expansion and actually looks like this. The action looks like this. Pi nu over 2 integral over space trace diffusion constant. So what happens with this gradient q squared term? If instead of q you put this matrix, actually you act with a gradient on W and then you square it. And you get gradient of B squared times gradient of B. That's it. All other terms are higher than of the second order. So this is the only term of the second order. And with the next one, with this one, what you get is minus I omega B dagger B. That's it. So again, you take this Q matrix, you multiply it with lambda, which cancels this lambda in front, and then you take a trace. Trace of unity is a constant. You throw it in the window. Trace of W is 0. Look at the W. Its trace is 0. And trace of W squared is B dagger B. So within this perturbation theory, up to the second order in the deviations from the North Pole, from Q equals lambda, you get a quadratic action. Now it's the action written in terms of B, and there are no restrictions on B. B is just any matrix. Q was restricted, B is free, but it's an expansion. It's not the exact action, it's an expansion, but it looks like a quadratic action, so it's Gaussian, it's a non-interacting theory. You can just, it's a quadratic form that you can easily diagonalize, and you know the propagators, all the averages in terms of B, anything. In particular, you can find an average of two matrices B, and actually I will just write the answer. Bij star times Bij. This is the only average that this is not 0. It's just the eigenvalue of this quadratic form. The eigenvalue, the inverse eigenvalue. So we inverted pi nu over 2 becomes 2 over pi nu. And the inversion of this thing is dq squared minus I omega. This is exactly the diffusion propagator. So small fluctuations of matrix Q near the matrix lambda, near the North Pole, translates these fluctuations are pictured as diffusons. Their propagator is the diffusion propagator. And actually B is a matrix, so I have indices ij, and since I have a trace of B dagger B here, it means that any pair of indices ij is correlated only with B with the same indices, but not with B with any other indices. So I can draw this propagator exactly as we usually draw a diffusion. It's a double line with some ladder inside. And we have indices ij on one end and the same indices ij on the other end. It's like a diffusion with two green functions, two electrons, one taken from replica number I, the other one taken from replica number j, and they are perfectly correlated because they see the same realization of disorder. So this is like B and B star with indices ij. I have a diagrammatic representation of this average, which is a propagator which has this dependence on Q and omega.
What is
What?
So formally speaking, you have the indices at each line, and they contract.
Well, formally speaking, you have I, J, K, L for indices,
Yes.
and then here you have delta of I, L, delta of K, J, which means that this index should coincide with that index, this index should coincide with that
I mean,
index.
like the lines, the vertical lines.
Oh, they're not actually present in the section. It's just to make it look like a diffusion. Originally, they were impurities. They were individual impurities.
Yes, and I don't understand what they're now.
Now you don't need to. You can think of this like just some shaded area. This is just it's a ribbon. You have a ribbon which represents a diffusion. This ribbon has one index on one edge, the other index on the other edge.
How do we know that this is a diffusion, not a Cooper?
Oh, that's a nice question because this sigma model, I forgot to say, is called a sigma model of a unitary class, which is a sigma model that knows only about diffusons, and you will know that this is a diffusion only when you study what is the other sigma model which also contains Cooperons. In a sense, look, Cooperon diffusons are always present in any model. They are related to the conservation of the number of particles. Cooperons are present only when you have time reversal symmetry. In a sense, when we derived this model, we didn't use time reversal symmetry in any form, which means that Cooperons do not appear inside such a model. But it's like it's not a proof of the statement, of course. It's like
Could you explain
proof of
why this correlator of 2B, which is just the perturbations to Q, are somehow connected with the diffusion?
just looking at the equation.
Yeah, okay, but we just calculated something and get that diffusion. And
Okay, you can look at it from some abstract viewpoint. We have a disordered system. We describe it with the action. We do some set of steps. We arrive at this action for the matrix Q, and this action within some perturbation theory in the zero order contains such propagators. You may not call them diffusons if you don't like. Just call them propagators of the sigma model in this limit. You can then derive from this sigma model some measurable things, and you will see that these measurable things correspond to what we've previously calculated with diagrams with diffusons one-to-one. So in a sense, it's just a terminology. Because it looks like a diffusion, we will also call it a diffusion. And everywhere where it appears, you can do the same thing without a sigma model with usual diffusons and get the same result. Just going through sigma model is actually easier. That's it. You can also calculate from the sigma model the real diffusion propagator. What is the correlate of density at one point with the density at the other point? And it will be still the same thing. But it's, yeah.
I mean, big conceptual question. In the end of the day, we want to calculate some observables, right? Like
Yeah.
conductivity or something. And before that, we expressed them via degree functions, more or less.
Yeah, with a Kubo formula.
Yes, yes. And now, and degree functions, we got like diffusons and stuff like this.
Mm-hmm.
And now, instead of all that, we have the object which is called B. So
Mm-hmm.
will we somehow derive the observables via the B?
Yes.
Okay.
More, even better, we will derive them today, hopefully.
is there any single relation between true green functions and Q?
Yes.
Have we discussed it today?
No, we will never discuss it. Well, let me put it this way. You can invent some relation between Q and green function, and I know people who are using such relations quite extensively, but I'm not one of those people, and I believe you can do everything without assuming that Q is some kind of a green function.
No, I'm just meaning that
Yes.
system, and we
Okay, that's a nice point. This is what I tried to tell to Dimo, but let's put it. Let me say it once again. Imagine you want to calculate a very well observable quantity, which is a real diffusion correlator, as we had with the Kubo formula with two green functions. You take your original action for the sigma model, not for the sigma model, the original action in terms of 5 fields, and you have the exponential of the action, and you add in the pre-exponent the 5 fields such that it will give you the average product of two green functions. Then you repeat the whole derivation of the sigma model, all the 8 steps, not just for the exponential, but for the exponential with this pre-exponent. And then in the end, what you get will be, again, the exponent of this action, and then there will be some pre-exponent in terms of Q. And then you will calculate this thing in terms of Q, and you will get this object once again.
Yeah, okay, so my question is, there is simple recipe how to
No.
describe object
Well,
with view?
simple recipe is include a source term in your action from the very beginning, derive the sigma model with source terms, then take the derivative with respect to source term, and you will generate all these operators in terms of Q. But that's easy to say, but not very easy to do. You can as well do it without source terms. Yeah, so actually what I will present here does not require this. We will do the calculation only with the action, and this will be already enough for our purposes. So, once again, perturbation theory, Q is close to lambda. Deviations of Q from lambda are quantified with these matrices B and B dagger. We have quadratic action for B, and the propagator looks like a diffusion. So in this quadratic order, actually our sigma model is equivalent, once again, to classical theory. When diffusion equation is exact, there are no quantum corrections. This is all you need to know in a classical physics. If you want to produce some corrections, some quantum corrections to this thing, you just do this expansion in W to the next order. You live on the sphere. You did something near the North Pole, so you can do expansion to larger and larger orders, exploring your space further and further from the North Pole. But before we do this, first of all, I should erase finally something from here.
Sorry, yes. So Q is Lie group. Is Q?
Yes. No, wait. U to N is a Lie group.
Q.
Q is a point of a coset space which is not a group. It's a factor space when one group is divided by a not normal subgroup. So it's a manifold. It's a curved manifold. Just imagine a sphere. A sphere is not a group because if you have 2 points on the sphere, you have no idea how to multiply them. Right? How to multiply the North Pole by the point here in Ljubljana. What's the product of these 2 points? What you can multiply rotations. If you have a rotation, this is a group. This U group is the rotations of the sphere. You can multiply them by just doing 2 rotations in sequence. But Q is already, so when you factorize all possible rotations by the rotations that have 1 point fixed, what you get in the end is just the space of these points, of these different points. And they cannot be directly multiplied. That's why this is not a group. Okay, so let me really erase a little bit. Yeah.
Yeah, I have just a little conceptual question. So, I thought this electron in 2-dimensional material with some delta potential impurities, right?
With the random impurities that have a delta function as their correlator, not a delta function potential. Correlation of 2 V's is a delta function.
But I thought also, we discussed this a little bit also, that some people run these potentials as delta functions times
some people, but not me.
Okay, because wait, that's the setup that we are dealing with. And
Yeah.
where in this setup there is a sphere on which we are finding some points?
Look, we had a random potential in real space, and we had a fields phi, these Grassmann-valued fields phi that live in that space and that describe the wave function of electrons. And then we did 8 steps to arrive to this action, and within these steps we introduced a new field Q, and we integrated out the old field phi. So this Q has nothing to do with the original. It's, in a sense, it's a, I'm not sure if I can say it like that, but it's in a sense a dual field to the original phi field.
In the original setup, there should be something that is, after this transformation here, present.
No, it should not. I mean, there is a derivation, one by one step, which we wasted the whole last lecture doing. So as long as you understand these steps, you can trace it back and build some intuition what you think about this Q matrix. But I have no such an intuition. For me, Q matrix is just a field, it's something that lives on this sphere and obeys something that looks like a diffusion equation. Okay, so let's do one last trick before any actual calculation. Any calculation, I mean, we will do particular thing in this perturbation theory, but before doing such an actual calculation, I need to tell you what happens when we expand to the next orders. And actually, here there is one very important advantage of a sigma model that you don't have when you deal with diagrams. The advantage is the following. Look, I told you that Q matrix is like lambda times the exponent of W. Actually, you can do better. You can say that Q matrix is lambda times some function of W. You can generalize, instead of exponential function, you can use some other function. This function of W obeys a certain constraint, namely, if you multiply f of W and f of minus W, it should be always unity. If you impose such a constraint, then Q squared will be automatically a unit matrix. Q squared, lambda F. W anti-commutes with lambda. Look, Q squared equals lambda F of W, right? Now here in the middle, I have F of W with 2 lambdas on both sides. And since W anti-commutes with lambda, which I still did not raise, this thing in the middle is F of minus W. So the product F of minus W times F of W must be 1, then Q squared will be also 1. And exponential is clearly satisfying this condition. Yeah? Exponent of W times exponent of minus W is 1. So the nice thing about sigma model is that you can use, instead of exponential, you can use any other function that has this property. You choose any other function, and your observable results, which you compute from this perturbation theory, should not depend on this choice. This.
So you write action as a function of some manifold, and then you put nonlinear constraint on the manifold.
Yeah, so.
And then we say that you find fixed point and find perturbation stuff.
Yeah.
How can I intuitively understand that it will work only on nonlinear constraints?
No. This action itself is only correct for matrix Q that obeys this constraint. This action has no meaning. I mean, it was derived during the derivation we took a saddle point approximation. There were many saddle points. We say they are all forming a manifold, and Q belongs to this manifold. So this action is the action on this manifold. It's no meaning if you say that Q matrix violates this constraint. It just has no meaning. This action was derived only for Q matrices that obey this constraint. That's why you say Q matrix is bound to this sphere. It can move only within it. It cannot go out. And within this sphere, you can use such an action to describe it. Okay, so as I said, any function f of w is as good as any other as long as they obey this constraint. And actually, when we do this perturbation theory, we will replace integrals. We have integrals over the matrix Q. It's our action. And we should take something like path integrals or functional integrals or usual integrals over all possible configurations of Q. So we will replace integral over Q with an integral over W. W is just it's called parametrization. We have a manifold, and we can say that each point on the manifold is some matrix Q, or we can as well say that each point on the manifold is some value of W. So it's like a change of variables in the integral. And we will do this because in W, for example, this thing is quadratic. B and W are linearly related. That thing is quadratic. And usually when you do such a change of variables, you also have something which is called a Jacobian, which is a function of W. Yeah. So this Jacobian actually depends on which function f you chose. For some different functions, f is like different coordinate systems on this manifold, and for some coordinate systems you have non-trivial volume element, and for some others you have easier volume element. So first choice, f of W equals the exponent of W. This is just what we did here.
So this is actually precise.
What is actually precise?
That f W equals exponent of W. We didn't actually use any perturbation yet. We just
Sorry.
said that t can be written as e to the power of W over 2, and this is true for any t, right?
Yes, and this is also true, and this follows from that one.
Yes, and this is true for any t, for any q.
Yes. Then we say that actually we can use some other function, not exponential. But exponential we can also use.
Approximately.
No, exactly. That's the point. Look.
I mean, like, wait. Sorry.
Dima. Imagine a sphere.
I understand. Yes.
You have coordinates on this sphere, longitude and latitude, right? You can use some other coordinates.
Yes, the question is way more simple. But anyway, I just take t equals to e to the power of w over 2. They take the fact that...
You mean this equals that?
Yes, and it's
Yeah, this is exact, of course.
okay.
Because
Now-
W anticommutes with lambda.
Yes, so this is exact. And any other parameterization would be not exact.
No, because lambda anticommutes with W. So when, let me write it once again.
Okay,
Let me write it once again. Lambda f of W times lambda equals lambda times f of minus W. This is true for any function f. Any function
yes,
f.
Okay, yes.
And this is the generalization of what you had here. Okay, so what should we take as such a function? Of course, we can take the exponential because we started with it. But it turns out that this exponential function is not very convenient for the following reason, that the corresponding Jacobian is a complicated thing. It's not equal just to unity. So you need not only the action written in terms of W, you also have to compute the Jacobian, and you have to use it in your perturbative calculation. So this is the exponential parameterization. It's the easiest one from the mathematical viewpoint, because this is how usually you define Lie groups and work with them. And this is a very simple function indeed. But the corresponding Jacobian is actually not so easy, and there are better choices how to do this. So second choice, which was second choice, f of w equals square root of 1 plus w squared plus w. You can check that this product is 1. It's very easy. This particular function of w has its own advantages. Namely, the main advantage is if you do it this way, each diagram that you derive from the sigma model will be exactly equal to a certain diagram derived from the usual diffusons and sometimes couperons. So this is the parameterization that allows you to restore the original diagrammatic technique from the sigma model, which we will not do, of course, but it's nice to know that such a thing exists. And it also has a non-trivial Jacobian. So this thing allows you to restore original diagrams. Let me remind you one thing. When we did calculation with the diagrams of the quantum correction to the diffusion propagator, we had a problem that we have a Hikami box, and then there was some extra number 1 which had to be cancelled such that everything converges and does not violate gauge symmetry. So this is exactly what happens when you have a parameterization with Jacobian that is not 1. If you do the same calculation from the sigma model using this function f, you will find exactly the same expressions, including this extra number 1, which is the wrong thing. But then if you take into account that Jacobian is not 1, there are some also contributions. When you expand this thing in W, it will cancel this 1, and you will get the correct result. So what we have seen in usual diagrammatic calculation, when we have this extra 1 that had to be cancelled, is exactly it is related to this fact that Jacobian here is not 1. It's a different manifestation of the same effect, if you like.
Actually, is there a way to see that you will get original diagrams to any order of the perturbation series if you continue to higher number of loops?
That's a good point. I don't know, I didn't check this, but I know there is a paper, the original one, authored by Hikami, who suggested this parameterization, and that contains this statement. I just don't remember how well it was proven there. Maybe he checked for a few first orders only.
So, but how would you think about this statement? Like, how would you prove it if you want to prove in general for any order?
I don't know. I haven't think of it yet. That's a good point. Maybe there is a way. I have to look into that paper. Maybe it's already written. Maybe this proof is already there. But this is what I was told by my older colleagues, so I just keep repeating it. Yeah. Then there is a third choice, which is quite often used. This is called, I forget, they all have names. This is called exponential parameterization. This is called square root parameterization. And this one, which I'm writing right now, is called the rational parameterization because it's a rational function of w. 1 plus w over 2, 1 minus w over 2. This one is quite a simple function, and this parameterization is used in some calculations. It has a nice feature that for this parameterization, the Jacobian is unity. So you don't need to take into account any strange contributions and cancel any strange divergences. it will never produce them. And finally, the fourth case, this is called rational, exponential, square root, rational. And there is a last one, the last one in this list, but not the last one in general, is the following. It's, oh, that's tricky. 1 plus w times the square root of 1 plus w squared over 4 plus w squared over 2. I am sorry, I probably should remove this somehow. Yeah. Plus w squared over 2. Or you can write the same thing as a total square. It's w over 2 plus the square root of 1 plus w squared over 4. The whole thing squared. It's just the same function. So this parameterization is the trickiest function of all of this, right? It looks in the most strange way, but first of all, it also has the Jacobian, which is exactly 1, and it's much easier to do calculations in this case with things that have this property. And second, if you look at this expansion here, you will see that it has 1, it has w squared, and all other terms, if you expand the square root in w, all other terms are odd functions of w. They are w to odd powers. It has only one term with an even power of w. All other terms have odd power, which means that in this particular parameterization, if you take trace lambda q, it exactly is, who knows what it is? It's 1/2 trace lambda w squared, right? I just take this. This is almost q. If I multiply with lambda, it will be q. If I multiply q, so it's just trace of this function. So the nice thing about this parameterization is not only that it has j equals 1, Jacobian equals to 1, also the potential term in the action, this potential term, is exactly quadratic. There are no further powers of w. So if for some reason you study the problem where gradients are not important and only the potential term is important, this is the best you can do. And actually I have no idea why I bother you with all these functions, because we will never use any of them.
Why we use it, what do you want to do with it? I thought next step will be that you will obtain some corrections to this.
Exactly, this will be the next step.
And you will use something.
I will use something, but not any of these. I will use something number 5, which is not yet written. Yeah, I'm just showing you this just to tell you that sigma model is easier in some sense because you can choose the function, the parameterization you like on this manifold, such that you simplify the calculation as much as you can. And when you do it with diagrams, you don't have this freedom. You have, well, the diagrams are like this, and you have to compute them. It's like fixing one of these choices. And once again, you can use any of these things, and when you complete the calculation, the result should not depend on which one you used. And this is another nice way to do calculations. You do them in several of them, then compare. If the results do not coincide, then you know there is a mistake. Okay, so I promised you to show some explicit calculation within this perturbation theory of something interesting, and this was the only reason why Dima is still here. And yeah, so what can we do? First of all, as was already discussed shortly, this model contains only diffusons. There are no couperons. That's why it's not possible to calculate corrections that we did before with diagrams when it was a couperon loop, because there are no couperons in this model, only diffusons. On the other hand, as was also mentioned a couple of lectures ago, there is a specific situation which is called unitary, when the quantum correction to conductivity is particularly small. It's not zero, but it's small. And it is exactly this situation for which such a model is applied. It's a unitary sigma model, meaning it contains only diffusons, there is no time reversal symmetry. So we can actually use this model to derive that small correction to conductivity that I have mentioned 2 lectures ago, but never really derived. And actually it's much, much easier with the sigma model than with the original diagrams. That's why I didn't show you how to do it with diagrams, but I will show how to do it with the sigma model. But to make this calculation even easier, as mentioned, we should use not any one of these 4 representations. We will use actually the 5th one, which is very special, and I will write it right here on top. And it will look in a very, well, it will look a bit unusual first, but just bear with me. So we will use something that is called Dyson-Maleev parametrization. It has a name. And originally it was done by Dyson and Maleev, but not for the sigma model. They didn't know what a sigma model is, or at least maybe they knew, but they had other things to work with. So it was for some spin operators, and then later it was adapted for the sigma model by one of our guests sitting over there. And it's the parameterization like this. We write the Q matrix, which is a matrix in retarded advanced space. And now I quote Dima directly from your paper. 1 minus B. Okay, well, sorry. Let's do it step by step. So when Q equals lambda, when we're exactly at the North Pole, Q is 1 minus 1, right? There's nothing else. 1 minus 1. Then there is a linear term plus W, sorry, this is T, and Q is 1 plus W. And W was B dagger, B minus B dagger, which is erased, so I will put it here. B minus B dagger. Then there is a next term, which is W squared over 2. Sorry, it's barely visible. I add it here, and I have minus B dagger over 2. Can you see what's written here?
Not on the camera.
Okay. And plus B dagger B over 2 in this part.
Could you explain that,
Sorry?
please? Could you explain it a bit? It's not possible to see what's in one.
If I try to clean it, it will become even worse, I believe. Or maybe not that bad. Okay, so it's, yeah. It's B times B dagger over 2. This is minus. So once again, we have lambda, 1 minus 1. This is 0 order. Then we have lambda plus W and plus W squared over 2. This is actually what we had here. Plus W means B here and minus B dagger here. Then plus W squared over 2 produces these 2 diagonal terms. And actually, I forgot to tell you, but all these 4 functions that we had before, if you expand them in series, they all start with these 3 things. they're only distinguished by the cubic term and further. So when I write it this way, I have not yet specified the parameterization. But as long as I write the cubic term, it will fix one of them. And as I said, it will be not one of these, but it will be like that. It's a cubic term minus b dagger b, 3 matrices, divided by 4, and that's it. This is called Tyson-Maliev parameterization of the Q matrix. I will give you a few seconds to appreciate the beauty.
To square this matrix.
Hmm?
To calculate the square of this matrix.
Yeah. The nice thing, this is just a finite expression, finite polynomial up to quadratic order and up to cubic order here. But it turns out that if you compute the square of this matrix, explicitly just multiply the matrix by itself, it's exactly 1. You don't need any further terms.
So this is only expansion up to third order.
It's exact. Once again, q squared exactly equals 1. You don't need all further orders are 0. This is the exact thing, but it comes at a cost. It's not for free. It's not for free that when you can take the square root of matrix 1 and get a finite polynomial. The cost is that this matrix explicitly is not Hermitian, because this part, so b and b dagger, these two are actually, sorry, that's a misprint. There is no minus here. There's no minus here. All the rest is correct. There is no minus here. So this is b dagger here and b, but that part has no counterpart here, so it's not Hermitian. This matrix is not Hermitian. Anyway, it turns out that you can still do all the calculations and perturbatively, and as long as you integrate and integrals converge, you do obtain correct results. And why? I can give you a simple example, which I already gave before. Imagine you have an integral like exponent of minus x squared, which is square root of pi. It converges, it's a number, and x is a real variable. You integrate over a real variable. If you shift the variable, if you write x plus I plus something imaginary, you violate this principle. X plus I is not a real number. But the integral is still the same because it's just the shift of the contour. So the same here. We violate the condition that Q is Hermitian. Hermitian is like on the matrix language the same as saying real for numbers. So we violate this hermiticity, but as long as integrals converge and everything is nice, we will recover all the same results. So, Dyson-Maliev parameterization. Q squared equals 1, the explicit form of the matrix, and guess what the Jacobian is for this parameterization. Jacobian is 1. You don't have any tricks with that thing. I wish I had a better board because I need to write quite a lot and I don't have any space for this, any clean space. Okay, let me erase this. You know, this board is almost intact, but the duster becomes, I mean, it breaks down due to this process. Okay, so what we do, we take this action, we take this Q matrix, we substitute it here, compute the square, the gradient square, take the trace, and we find this action in terms of B and B dagger. And, or actually I can do it on that part of the board, because look, I here already have the action which contains quadratic terms in the gradients and in the potential. And actually for this parameterization it will be exactly the same. These two terms will not change, because they come from these quadratic terms here, which are the same in all parameterizations. All parameterizations have the same expansion up to quadratic terms, and they all have this quadratic part of the action. So what will change will be the third term, which contains the diffusion constant divided by 4, B dagger gradient B squared. That's it, nothing else. So we have a cubic term inside the Q matrix. So from this term we will have something of the fourth order in B fields, B dagger gradient B squared. But there are no terms of even higher order, because our Q matrix, thanks a lot, because our Q matrix does not contain terms of the high order. Or you take this Q matrix and you square it. I mean, you take the gradient and you square, and there is a part when you multiply this B dagger with this one from the other Q matrix. So you get the full term like this.
This is again the exact action.
Yes, this is the exact action. It's no longer Gaussian, because it's not quadratic, it has a fourth order term, so it's not exactly solvable, but it's very easy. It tells us that we have diffusons like this, propagators, and these diffusons can interact with each other, and the interaction vertex is what is written here. It's an object like this, the point where 4 diffusons meet. Look, again, it's like an indices. I, J, K, K, L, L, I. When you have a trace and the product of 4 matrices, you can say that they are contracted like these ribbons, and whenever this line is attached to this line, you have the repeated index. So this is one matrix, B dagger, gradient B dagger, gradient B. And then you have a trace, and Ij is to this matrix, Jk is to this matrix, Kl is to this matrix. So I will actually represent this vertex. It's also proportional to pi nu d over 8. I will also draw this vertex with such a dash line here and here. It just shows that you should take a gradient. This is a gradient B coming from here, but this is a B dagger without a gradient coming from here. And then gradient B from here, B dagger from there. B has no restrictions. B is an n times n complex matrix point. N squared complex numbers. You have a question? No, any matrix.
But it has also spin or orbit indices.
No. The original Q matrix, or W, also has retarded advanced structure. This one, retarded advanced. And B is like a single block of this matrix. It doesn't have such a structure. It's just n times n. This one is 2n by 2n, and B is n times n. Okay, so let me try. Oh, that's much better. Thank you. I mean, for erasing. So, as I said, we do have the propagator, which is a diffuson, and it's shown here. This is a diffuson, yeah, the correlator of 2 B fields. And I would like to compute a correction to this diffuson due to this interaction vertex. So I say, now, this is a perturbation theory. This object is small, this interaction is weak, so I will take it as a small perturbation. I have the exponent of my action. I will expand it, assuming this is small, we'll take it out of the exponent, average with respect to with the Gaussian action, and then what is left will be put back into exponent. This is how you do perturbation theory in field theories. And this is how you normally get diagrams in field theories. So I have a vertex. I have a vertex. This is my vertex. And this vertex has two gradients. I will put it here and here. And I'm out of chalk, which is nice. Take a new one. Then I have another vertex. I do it to the second order. I have another vertex, and I have two gradients here and here. So I do second order perturbation theory. I take this trace from my exponent twice.
But maybe you first show that the first order doesn't produce any meaningful diagrams.
Okay.
Because naively I would try just to put first one vertex and connect the two ends.
Don't pretend to be so naive. Yeah, right. In the first order, we have just one vertex. It has four fields, B, 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 B. And we say, let's contract two of them, replace them with the average. And this will produce some correction to the remaining two. So we do contract them, which means we insert here this ribbon, this diffusion. And then we say, okay, this is now a diagram like a self-energy.
But the line have directions, right? So you cannot like put a Möbius, put them in a Möbius way.
Yeah, this is true. That's why I show you. I draw it in the correct way.
Yeah.
You cannot flip it because it's not a Couperon. You can flip a Couperon, but this one is a diffusion. So you have B and B dagger here, actually gradient B and B dagger. But the problem with this diagram is that you have this loop inside which is detached from everything else. And as I explained, each line carries its own replica index. This line carries replica index I. This line carries replica index J. Inside the trace, when I contract two matrices, when I multiply two matrices, I say that the last index of one matrix equals the first index of the next matrix, so they are on the same line. So since I have this closed line here, let's say it's I, J, J, and so on, I have summation over this index J, which goes inside this loop. And this summation produces the total number of replicas, because I sum from 1 to n over all replicas, which will be, this total number of replicas will be the prefactor to this whole diagram. And in the very end, when we take the replica limit, when we say n goes to 0, this diagram will disappear. So this diagram actually does not contribute to anything. Another way to see this, if you try to do the same diagram with real green functions, not from the sigma model, you say this is a green function, this is a green function, this is a diffusion. I have impurity lines here. And then I will ask you, what's this fermionic loop you have, which is attached to the rest of your diagram only by dashed lines. We never had a diagram like this before. Because in usual diagrammatic technique, what we do, we first draw green functions, then we put impurities, and then we average over disorder, which means connect impurities with the dashed lines. So you can never generate a new green function that was not there originally. And here you have some fermionic loop, which is completely detached from your system and connected only by these dashed lines. This is not how it works. So this never appears in the usual diagrammatic technique, and this will be cancelled in this technique because sum over J gives you the number of replicas, which in the end goes to 0. That's why we should go to the...
What if you connect the top and the bottom?
You cannot connect two B's or two B daggers. You should connect B to B dagger. You have a star here. B dagger, B dagger. Okay, so this diagram does not exist or provides a 0 result, so I will remove at least the diffusion from this diagram. And I will go to the second order with two such vertices. Let me draw the second one once again. And I will try to average them. I have 4 B fields here, 4 B fields here, so I will average 6 of them, and 2 will remain free. Sorry? Yep.
May I ask last question about the previous diagram? So we have we have constructed this loop, right?
Yeah.
And that corresponds to the fact that we will have some like Bij, nabla, B dagger Ij, nabla, B,
You can-
G, something K.
You can do it without drawing diagrams, just algebraically. You have trace, look, you have trace, B dagger, nabla, B, B dagger, nabla, B, and you replace these two B's with their average, with this object. That's it. And then it's a function of 2 remaining B's. That's what was that diagram. But then inside this trace, this trace is like having indices I, J, K, K, L, L, M. And then you look here. Well, it's dagger, so you should transpose it. And you see that this index L, you have a summation over L, and this object equals the same thing for all values of L, so it multiplies by the number of replicas. And I can do this, I also draw a diagram, but you can do it like that. You can say this trace twice, trace times trace, and then you connect different B's and say I average this and that. So the only way I checked many times myself, the only way to connect these two vertices such that you do not produce any detached loops that provide you the factor n that will in the end cancel the diagram, the only way is to attach this point directly to this point. This upper thing you attach to this one below, and this one is attached to the one above. This is the only way. And yeah, look, I have gradients here, and in that vertex I have gradients here. So gradient always applies to B and not to B dagger. So I should always attach the line with a gradient to the line without a gradient. This is the only way.
So it's not possible to take like 1,000 such vertices and connect them?
Yes, it's possible if you want to go to perturbation theory to the order 1,000.
Okay. So this is the only way
If you have 2 vertices in the second order. Yeah, so I have two fields that are not averaged, B here and B dagger here, and this whole object actually is a self-energy for the diffusion. So I have a diffusion, which is this ribbon, and I can insert these strange things once, twice, 3 times, 4 times, as we did before. Yes?
Just a little bit closer, can you repeat, perturbation theory is done with respect to which parameter?
This will be later.
How can you see from this diagram that second order?
Actually, the parameter of the perturbation theory, in a sense, is this product, nu times d. You see, nu d goes to the denominator. It's a large parameter, so each diffusion is small. Each vertex has the same product, nu times d in the numerator, so each vertex is large. But I have only 2 vertices here and 3 diffusions. That's why it's a small thing. I have nu d squared in the numerator and cube in the denominator. And the good way to know which diagram is larger and which one is smaller actually is to count the number of loops. This is a loop expansion. This is a two-loop diagram. It has two loops. Yeah, just look at it. It has two loops, right? Each extra loop adds you this product nu and d in the denominator. Because inside the loop there is this Euler identity, I believe. Yeah. Then when you have a graph, you can compare the number of faces, or not a graph, or some.
But now it's not a planar diagram. So
Yeah, but for Euler, it's not important, planar or not.
I thought, well,
I mean, there is an identity between the number of vertices, the number of, what's the proper name for this? Edges, and the number of faces. So the number of loops is the number of faces, and each edge and each vertex have some factor. So you, using this identity, you can see that the number of loops always gives you the order of the perturbation theory. Yeah, so let's finally calculate. It's not so easy to calculate. We still have to do this, and we have only 5 minutes left. How to compute such a diagram? Look, it's very simple if you do the calculation in, not in momentum representation, but in real space representation. This is the diffusion propagator in momentum representation. It has Q inside. Now, if you look at this diagram, it has 3 diffusons going from this point to this point. This is one of them. This is the second. And this one is the third. And they all start at the same point, and they all end also at the same point. So in real space representation, it's like 3 times the same diffusion. Now the question, on the very first lecture, I gave you a homework to calculate the diffusion in real space representation. Does anybody know the answer?
Which number of dimensions?
2.
Yes.
It was the point number 3. It was 1, 3, then 2 with a star, with an asterisk. Yeah, I'm joking. Of course, I will now show you how to do this. In general, if you have that object here and you try to do Fourier transform, you get what is called the Bessel function. But we will not bother ourselves with the Bessel function. We compute diffusion in real space. And the object is like that. 2 over pi nu, right? It's this prefactor. Integral over all momenta q, d2q, two-dimensional integral in momentum space, 2 pi squared, e to power I q r divided by dq squared, and I will simplify my life greatly by just neglecting omega. You can remember when we computed weak localization corrections with diagrams, we also neglected omega. So that's fine. We don't need it. So omega is needed only to cut the integral at smallest values of q, and we can as well cut it by the system size. Say L inverse is our system size, right? Or wrong? Small values of q, yeah, that's right. And then we should cut it from the upper bound, and it actually, if there is no this exponent, if you just forget about this exponential, it's a logarithmic integral. It's 2q's divided by 2q's. It's a logarithmic integral. And this r, this distance r, which is the argument, defines where we should, defines the shortest scale at which we should cut this logarithm. So in fact, what we get here is 2 over pi nu, 2 pi cancelled. That's why I have 1 over 2 pi d. And then I have a logarithm which has r inverse divided by L inverse, which is r divided by L with a minus sign. Minus. This is how you do your homework.
How did you select upper bound?
Upper bound, so there is no upper bound here, but we have this exponential which at large values of q starts oscillating. So it oscillates with q, and the typical scale at which it oscillates is inverse r. That's why this inverse r effectively is the upper bound for this logarithm. So this is a single diffusion. I can cancel 2, of course, so it's pi squared nu d logarithm. And minus. Now this diagram, I will call it gamma. Gamma is my diagram because it's a self-energy for the diffusion. It has 2 vertices, 1 and 2, and each vertex has this pi nu d over 8. Gamma equals pi nu d, okay, over 8 is too much, over 4. Over 4 squared, because I have 2 of them, and over 4 because each vertex I can actually connect in 2 different ways. I mean, I can interchange this 2 and this 2, and the same here. That's why it's the usual thing in all integrals like this. When you have something of the order n, you have 1 over n factorial, I believe, in front, and this factorial term cancels when you do diagrams, because you can insert this thing n factorial ways. So this is a prefactor, and then I have 3 diffusons, 1, 2, 3 diffusons. And then with these 3 diffusons, I will have a real space integral, 2-dimensional integral over r. R is just the distance from this point to this point. It's the distance. This is r from here to here. So if I put every diffusion in real space representation, I then have to integrate over the relative distance between these 2 points. So what I have inside, I have diffusion number 1, this one. Oh, no, sorry, this one is a diffusion with a gradient applied to it. And this is another diffusion with a gradient applied to it. So what I have here is the gradient of a diffusion of r squared. It's this 2 of these loops. And then I have the third diffusion, which also has a gradient d of r. And I should add a minus sign because it's a gradient taken from the other side. It's with an opposite sign. But this gradient, it's a vector. It's not yet contracted with anything. It should be contracted with this gradient, which stays outside, which attaches to the outer line. So I will do it a bit later. I want to know what my vertex gamma is actually on a given momentum. I want to add gamma, add my self-energy to the diffusion in momentum representation. So to know the momentum representation of this thing, I should do the inverse Fourier transform from real space back to momentum space. So there should be also e to power minus I q r here. And q is the external momentum that goes through this diagram. So actually this is not an integral over all distances, it's actually a Fourier transform. And now this external gradient with this q is just multiplication by q. So I can write here I q, and this is a vector q times vector nabla. I pick q from here and gradient of d from here, and I contract them because inside this vertex I have the contraction of these 2 gradients. I know this is not an easy thing, but honestly I am doing it right now from scratch, so.
I would personally prefer just to write it down as an integral from the very beginning and to see that IQ actually just drops as a factor.
okay, let me
But I mean, like, I
Let-
can do it by myself. Like,
let me put it this way. Gamma in real space representation does not contain any integral at all.
yes.
It's a function of a single distance, and it's just a product of three diffusons. And then when I convert it to a momentum space, I do Fourier transform. Now, this product of three diffusons, two of them have gradients acting on them and then contracted because they're contracted inside this vertex as vectors. And the third one has a gradient with a minus sign because it's on the other side. And it should be contracted to a gradient which is outside. And in real space representation, I still don't know what it is. It's like a differential operator. But when I convert to momentum space, it becomes Q, and I can contract it here. So it's very easy now. I mean, it's almost done. We are interested in this gamma of Q in the limit of small q. Q is very, 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 very small. So the last step to do is to take this exponential here and expand it assuming Q is small. Yes, I write 1 minus I Q R, and that's it. Expanded at small q, this is 0 order, the first order. If I just take 1 here, this integral will be 0 because it's a vector. And I integrate over all r, so it's 0. But if I take the first term, then I will get something which is non-zero and which is quadratic in q because I have one q here and the other one from here. So I will have my gamma of q, a quadratic function of q. It will be q squared times a number. And this q squared times a number will provide a correction to the diffusion constant as we did it before in one loop calculation. And this will be exactly the correction that I would like to find. So it remains to calculate this thing. It's extremely easy. Somebody tell me what's the gradient of logarithm? 1 over r, yeah, exactly. And somebody else tell me where should I write on this board? Probably here. So what I have now is minus pi nu d over 4 squared, that's fine, minus pi nu d over 4 squared, then 1 over r, then the integral, two-dimensional integral over r, and this is just 1 over r, so it's 1 over r squared, yeah, the square of this gradient. What about this gradient? It's just also 1 over r, yeah? So it's I, the scalar product q times r, divided by r squared, right? And this thing, from this part, I just take minus I QR, minus I and QR, and one other power of QR. Very nice. I, of course, got the wrong sign, because the gradient of logarithm, who told me that's 1 over r? It's minus logarithm. It's minus 1 over r. It's minus here. Then I have minus, and product of these two is also minus, so it's plus. Gamma is positive. Once again, pi nu d over 4 squared. 2 pi coming from this d to r, 2 pi. And qr squared is q squared times r squared divided by 2. Yeah, because cosine squared average is 1/2. So I have 1/2. And then I have q squared. And then I have r squared, r squared, r squared, r squared. I have a logarithm. And this logarithm it's the limits, how this distance between these 2 points changes. The shortest possible distance is L, is the mean free path, and the longest possible distance is the size of the sample, which is capital L, and that's it. This is the whole gamma of Q. And I really hope I did it all correctly. Oh, of course, I forgot that each diffusion also has this prefactor. Each diffusion has pi squared nu d in the denominator. Sorry, divided by pi squared nu d 3 times. So once again, if I cancel everything that can be cancelled, this should be equal to q squared logarithm L over L divided by 16 pi cube nu d. Pi squared divided by pi to power 6 is pi minus 4. Pi minus 3, pi cube is correct. 4 squared is 16 to cancel. Yeah, that's it. This is gamma, which should be added to the denominator of this expression. So inverse diffusion propagator is pi nu over 2 dq squared minus I omega. I just inversed this thing. And then I should put minus gamma to this object. Gamma is like a self-energy. So I should say, we did it before many times, right?
Minus gamma q squared.
Q squared is part of the gamma. And what I have doing this, I have pi nu over 2 q squared, and then I have diffusion constant and some correction to this diffusion constant, which is negative because minus gamma, and which equals all this thing other than q squared and pi nu over 2. So it is log L over L divided by 8 pi to power 4 nu squared, and I forgot what else. Nu squared d, yeah, exactly. And minus the term with omega. I'm just trying to say that the prefactor of q squared is the diffusion constant minus this correction. And this is the end already. I erase something which was not yet erased. So this is the correction to the diffusion constant, and we all know how to convert it into correction to conductivity. Just use the Einstein relation. Correction to conductivity, delta sigma, is E squared nu correction to the diffusion constant. And it equals, this is the correction to the diffusion constant. I should multiply it with E squared and with nu. So it's minus E squared over 8 pi to power 4. And then I have the product nu times d in the denominator. So this nu, one of the nu's cancels. I have nu times d. Nu times d, according to the Einstein's relation, is another E squared times conductivity. So I have just sigma here, sigma. And then logarithm of L over L. So actually it's electron charge power 4 in the numerator. So this is a negative weak localization correction to conductivity in the unitary class. And this is it's logarithmic as well as in any other class with this prefactor.
For other classes, it was like.
It didn't have this sigma here, it was just a number, e squared over 2 pi squared times logarithm. And this one has extra sigma in the denominator. Unitary. I will right now draw this plot once again, just to remind you how it looked like. So actually we are all more or less done. It's just this last plot. So this is sigma conductivity, and this is the beta function, which is the derivative of logarithm sigma with respect to logarithm of L. And we had 3 cases. One case, the one, second one, and the third one in between. This correction here was plus 1 over sigma. This one below was minus 1 over sigma. Well, not 1, it was just some number here, but never mind. And this was orthogonal, this lower one was orthogonal with weak localization. This is symplectic with weak anti-localization. And what we have right now calculated is the unitary, is the one between them, the one without couperons. And the correction here, just as we have found it, behaves as minus 1 over sigma squared. Because this is log sigma, so when I take the derivative, it's 1 over sigma times correction, so it's extra 1 over sigma. So this is unitary, and it's minus 1 over sigma squared. It's unitary. That's all for today. Thanks very much. Does anybody have any questions?